Bismillahirrahmanirrahim. I hope you guys are good at your places. Let's start with the lecture, which is analysis and design of slab. In reinforced concrete construction, slabs are used as flat and useful surfaces. A reinforced slab is a broad flat plate, usually horizontal, with top and bottom surfaces parallel or nearly so. Actually, slab is a plate element having one dimension very small if we compare with the other two dimension, and the smaller dimension is of course that is basically thickness. Slab may be supported by reinforced concrete beam, and these beams are normally casted monolithic with the slabs. It may be supported by masonry or reinforced concrete wall, or it may be supported by structural member made up of steel. It may be supported directly on columns, or it is continuously at the ground level. Now we have two different types of slab. One we called as one-way slab, and other we called as two-way slab. Now what are the one-way slab? If the slab resists the entire or major part of load by bending only in one direction, that particular type of slab we called as one-way slab. If slab is supported on all four sides, and support may be beam, may be wall or other structural element, shorter dimension divided by longer dimension, if that comes out to be less than 0.5, that particular type of slab we call as one-way slab. I will repeat again. If the shorter side of the slab divided by longer side of the slab is less than 0.5, that particular type of slab we call as one-way slab. Slab having support on less than 4 sides can be designed as one-way slab. Let's say slab is only supported by 2 sides. We need to design that slab as a one-way slab. Cantilever slab is always designed as one-way slab. For example, sunshades normally we design as a one-way slab. Now in case of one-way slab, how we decide the span? And span is important because we will put our main reinforcement parallel to the span. So if let's say we have supported longer edge, so this one is the smaller side and this side is the larger side, and if our slab is let's say supported on the longer side and only two sides are supported, then in between that distance we called as span. Let's say again we have two edges supported, this one and this one. Now this, the distance between the supported edge we call as span. Again I am repeating this thing. The distance between the supported edge, that we call as span, no matter whether it is shorter span or longer span. If our slab is supported on two sides, the distance between two sides, that particular we call as span. Let's say if our slab is supported on all the four sides, then shorter direction we call as span. Secondly, if we have a cantilever slab, then the unsupported span in the direction of the support, that we call as particularly span. We need span because main steel is only provided parallel to the slab. One-way slab is designed as a singly reinforced rectangular section. So H minimum for slab is different as compared with the beam, and this is the table which we got from the ACI. If we have simply supported span and we are using 300 grade, then we will use the minimum slab thickness equals to L by 25. If we are using grade 420, then we will use L by 20. Let's say we have a cantilever slab and we are using grade 300. The minimum slab thickness we can use is L by 12. Similarly, if we are using 420 grade for cantilever slab, we need to use minimum slab thickness equals to L by 10. Now, question is how we will get the effective span. Effective span is basically distance from center of the support to the center of the support. So, if let's say we have Ln, which is basically clear span length, right, and we will add h by 2 on one side and h by 2 on other side. So total effective span will be clear span plus the thickness of the slab, and that is basically distance from center of the support to the other center of the support. Now examples of one-way slab: shades in the roofing system, which is basically cantilever, needs to be designed as a one-way slab. Slab of staircase, cantilever retaining wall and footings normally we designed as a one-way slab. Now the spacing between the main reinforcement S max will be the minimum of the following criteria, and these are the criteria devised by the ACI code. So minimum of these four criteria will be our S max. So first one is 3 times H, where H is the thickness of slab. Second is 450 millimeter. Third is 158300 divided by Fy minus 2.5 cc, and cc is basically clear concrete cover. And fourth is 12600 divided by Fy. So out of these four criteria, whatever the minimum value we got, that is the maximum spacing of the reinforcement needs to be provided in the slab. Now the other reinforcement which we apply perpendicular to the main reinforcement, that we call as distribution steel or maybe temperature steel, or sometimes we call as shrinkage steel for slab. Shrinkage and temperature reinforcement is required at right angle to the main reinforcement to minimize the cracking and to tie the structure together to ensure it's acting as assumed in design. Top and bottom reinforcement are both effective in controlling the cracks. So this is the purpose of basically, in order to control the crack, we provided distribution steel. Now, how we will decide what is the area of steel for distribution or temperature steel? For grade 300, it is 0.002 B times H. B is normally we consider 1000 millimeter or 1 meter strip, and H is thickness of the slab. Similarly, for grade 420, it is 0.0018 B times H. If we are using some other grades rather than 300 and 420, then we will calculate rho is equals to 0.0018 multiplied by 420 divided by Fy. In no case distribution temperature or shrinkage should be less than 0.0014. The spacing of that distribution steel S max will be minimum of the two criteria. First criteria is 5 times H and second criteria is 450 millimeter. Normally in the field we provide 2 times H, but we can go with the ACI criteria as well. So minimum thickness for the slab is normally we use 100 millimeter for normal slabs, and we can go up till depending on the again loading condition, but we can go up till 9 inch. There is no hard and fast rule, but we can provide in residential building normally we provide 6 inches. Again it depends on the design and calculation. Next is check for shear. If 5e VC is greater than VU, meaning to that we do not need to provide any shear reinforcement. And in most of the time in slabs we do not need to provide shear reinforcement, as always 5e VC is greater than VU value. Now these are the steps which we followed in order to design the one-way slab. First of all, check whether our slab is one-way or two-way slab. If it is one-way, need to be designed as one-way. If it is two-way, then it needs to be designed as a two-way. Secondly, we need to calculate H minimum, which is the thickness of the slab. Normally not less than 110 millimeter for rooms and not less than 75 millimeter for sunshade. Afterwards, we will calculate the dead load acting on the slab, and dead load is actually load per unit area multiplied by 1 meter width. Then similarly, we will calculate the live load acting on the slab, and live load is load per unit area multiplied by a 1 meter strip. Then we will calculate the total factored load, as we know that 1.2 times dead plus 1.6 times live load, that is the total factored load. Then we will calculate the moments. Directly we can calculate, or we can use coefficient for continuous slab. I will discuss these coefficients later on. Then we will calculate the effective depth, meaning to that we need to deduct from the total slab thickness, we need to deduct the clear cover as well as half of the diameter of the bar we used. In case of slab, normally we prefer to use 10 millimeter or 13 millimeter bars. We need to check D needs to be greater than the minimum. Then we will calculate the area of steel required for 1 meter width. Then we will calculate the minimum distribution or temperature steel. We will calculate the diameter and spacing of the bar. And we will check the maximum spacing criteria. In case of continuous slab, we need to provide positive reinforcement as well as we need to provide negative reinforcement as well. Negative reinforcement, wherever we have support, there we need to provide the negative reinforcement as well. We need to check the shear as well, and as I said, most of the cases we do not need to provide shear reinforcement in the slab, as our this check 5E VC will be greater than the factored shear, which is VU. Then we will carry out our detailing and prepare the bar bending schedule. Proximate area of steel, normally it comes out to be 0.07 kg per millimeter per meter square. If slab thickness is 100 millimeter, then steel will be 7 kg per meter square. But this is approximate value. We need to calculate actually based on our loads. This is just for our reference value. Okay, so we end this lecture, and next time we will try to solve a one-way slab design example. Thank you very much.